This is part 1 of a review of Riemann sums and basic integrals. If you appreciate this content, please give it a like. Number 1. Use a trapezoidal sum or TSAM and the three subintervals indicated in the table to the right to approximate the integral of f of x from 1 to 10. We don't really know what f of x looks like, but imagine that it looks like this. Our goal is to approximate the integral of f of x from 1 to 10. That's the area under the curve on the interval from 1 to 10. Our strategy is to use these three trapezoids to estimate the area under the curve from 1 to 10. We will find the area of each trapezoid and then add them up. I like to use a chart like this one to organize my work, but this is optional. If you can set up your answer without making a chart, that's fine. I have a column for each interval indicated by the table, and since the area of a trapezoid is 1/2 base 1 plus base 2 times height, I need a row for base 1 plus base 2 and a row for the height. Focus on the first trapezoid. Base 1 and base 2 are the vertical sides. The length of base 1 will be the value of the function at 1. That's 12. So the length of this base is 12. The length of base 2 is the value of the function at 5. According to the table, that is 6. So base 1 plus base 2 is 18. The height of the rectangle will be the width of this interval. 5 minus 1 is 4, so that's the height of the trapezoid. Focus on the middle trapezoid. Base 1 will be the value of the function at 5, which is 6. Base 2 will be the value of the function at 7, which is 2. So base 1 plus base 2 is 8. The height of the trapezoid is the width of this interval, the distance between the bases. 7 minus 5 is 2. For the last trapezoid, base 1 will be the value of the function at 7, which is 2, and base 2 will be the value of the function at 10, which is 3. Base 1 plus base 2 is 5, and the height of the trapezoid is going to be 3. It's the distance between the bases, 10 minus 7. The integral of f of x from 1 to 10 will be approximately equal to the sum of the areas of these three trapezoids. The area of the first trapezoid is 1/2 base 1 plus base 2 times the height. And the area of the second trapezoid is 1/2 base 1 plus base 2 times the height. And the area of the third trapezoid is 1/2 base 1 plus base 2 times the height. You could simplify this answer. You could even use your calculator to do it, since this problem is calculator active. However, I encourage you to leave your answer like this. This is a full credit answer, so why waste your time simplifying, and why take the risk of making a careless mistake? But if you're curious, it comes out to be 51.5. By the way, you wouldn't really draw this picture. This is something you would visualize in your mind. I'm just showing it for instructional purposes. Number 2. Use the right rectangle approximation method and three subintervals of equal width to approximate the area under the graph of y equals x squared from x equals 0 to x equals 6. Here's a sketch of y equals x squared on the interval from 0 to 6. Our goal is to estimate the area under the curve on this interval. We have been instructed to use the right rectangle approximation method. That means we will use three right rectangles to approximate the area under the curve. A right rectangle is a rectangle drawn such that the right-hand side of the rectangle is on the curve. If we take the interval from 0 to 6 and we divide it into three subintervals of equal width, we get the interval from 0 to 2, 2 to 4, and 4 to 6. we will find the area of a rectangle in each one of these intervals. The area of a rectangle is base times height. So for my chart, I have a row for the base and a row for the height. Let's consider the rectangle on the interval from 2 to 4. The base of this rectangle is the width of the interval. 4 minus 2 is 2. These are equal width intervals. So each of these three rectangles will have the same width, the same base. 2, 2, and 2. So what about the height of the rectangle? Well, this was a right rectangle. So the height of this rectangle will be the value of the function at 4, the height of the curve on the right-hand side. If I plug 4 into the formula y equals x squared, that's y equals 4 squared, so the height of the rectangle is 16. Similarly, the height of the first rectangle will be the value of the function on the right side of the interval. So if I plug in 2, I get a height of 4. And the height of the rectangle on the third interval will be the value of the function at 6. And 6 squared is 36. So the area under the curve from 0 to 6 is approximately equal to the sum of the areas of the three rectangles. That's 2 times 4 plus 2 times 16 plus 2 times 36. This is a full credit answer, so I encourage you to leave your answer like this. But if you're curious, it does work out to be 112. Number 3, is your approximation using RRAM an overestimate or an underestimate of the true area? Explain in words how you know. I drew a roughly accurate sketch of y equals x squared, so we can easily see that a right rectangle is including this extra area that is not under the curve. So the RRAM is going to give us an overestimate. However, I want your explanation to be modeled after mine, almost word for word. Start by saying RRAM overestimates because. Then I want you to memorize the following information. Left and right rectangle approximation methods will over or underestimate depending on whether the curve is increasing or decreasing. The other methods, MRAM and TSAM, midpoint rectangle approximation method and trapezoidal sum approximation method, will overestimate or underestimate depending on the concavity of the curve. In this case, we are working with RRAM, so we will overestimate or underestimate depending on whether the curve is increasing or decreasing. Y equals x squared is increasing on the interval from 0 to 6. So we say RRAM overestimates because y equals x squared is increasing on the interval from 0 to 6. Let me point out two important things that must be included here. Do not say vague statements like the curve or the function right here. You need to name the specific curve that you're given. So say y equals x squared, or you could get away with just saying y. Also, you must mention the interval. It's increasing on the interval from 0 to 6. Y equals x squared is decreasing over here, so you can't just say y equals x squared is increasing. You have to be specific and say on the interval from 0 to 6. This is a full credit answer. Your answer should be almost word for word identical to mine. Number 4. Solve the differential equation dy dx equals x plus 4 sine x plus 3, given that the graph of the solution goes through the point 0, 2. We can find the general solution to this equation by taking the integral of both sides. The integral of dy dx is just y, and we will take the antiderivative of the right-hand side one term at a time. The antiderivative of x is going to be 1/2 x to the second power. we are doing the power rule of integration, where we increase the exponent by 1, and then we divide by that new exponent. For the next term, we're going to start by just bringing down the constant of 4, and then we move on to taking the antiderivative of sine x. I ask myself, the derivative of what is equal to sine? The derivative of cosine is negative sine. Therefore, the derivative of negative cosine will equal sine. So, negative cosine is the antiderivative of sine. The antiderivative of 3 is just 3x. And don't forget the constant of integration. We can use the initial condition 0, 2 to find the value of c. If we plug in the input value of 0, it should equal the output value of 2. Obviously, the value of this term and this term are both 0. But what is the cosine of 0? 0 radians is on the positive x-axis, and on the unit circle, it passes through the point 1, 0. On the unit circle, cosine is the x value, so the cosine of 0 radians is 1. So we get negative 4 times 1 plus c is equal to 2. Adding 4 to both sides, we're going to get c is equal to 6. Plugging 6 back in for c gives us this. This is the particular solution to the differential equation given the initial condition 0, 2. Number 5. Solve the differential equation f double prime of x equals 6x plus 3 using the initial conditions f prime of 1 equals 4 and f at 1 equals 7. The previous problem involved this notation, and solving the differential equation meant turning dy dx into just y. When the derivative is expressed as f prime, solving the differential equation means going from f prime to just f. But sometimes the differential equation starts with the second derivative. So in order to solve the equation, you first have to turn the second derivative into the first derivative. And then you can go ahead and solve by turning the first derivative into just y, or just f of x. In this case, we can find an expression for f prime by taking the antiderivative of both sides of this equation. The antiderivative of f double prime is f prime. We will use the power rule of integration on the term 6x. Increasing the exponent by 1 gives us x squared. And then dividing the coefficient by this new exponent, 6 divided by 2 is 3. The antiderivative of 3 is 3x. And don't forget to add the constant of integration. We can use the initial condition f prime at 1 equals 4 to find the value of c. At an input value of 1, f prime should equal 4. At an input value of 1, the left side of the equation becomes 3 plus c, and this is all equal to 4. This is 6 plus c is equal to 4, so subtracting 6 from both sides gives us c equals negative 2. Substituting negative 2 for c gives us the expression for f prime of x. Now we can find an expression for just f by taking the antiderivative of both sides of this equation. So f of x will equal, we increase the exponent by 1, so that will be x to the third power, and then we divide this coefficient by the new exponent. That's 1, and we don't need to write it. For the second term, we increase the exponent by 1, so this will be x squared, and then we divide the existing coefficient by that new exponent, so that's 3 over 2. The antiderivative of negative 2 is negative 2x, and now we need the constant of integration. But we already used the letter c, so this time we need to use something different, and let's call it d. We can use the initial condition f at 1 equals 7 to find the value of d. At an input value of 1, f should equal 7. At an input value of 1, the left side of the equation becomes this. So we have this is equal to 7. 1 and negative 2 combine to make negative 1. I would like to have like denominators here, so I'm going to write this 1 as 2 over 2. 3 over 2 minus 2 over 2 is 1 over 2. On the next step, I'm going to need like denominators. So let's write 7 as 14 over 2. Subtracting 1/2 from both sides, 14 over 2 minus 1 over 2 is 13 over 2. So the solution to the differential equation is f of x equals x to the third power plus 3/2 x squared minus 2x plus 13 over 2. Number 6. Given that the integral of f of x from 1 to 5 is equal to 5, and the integral of f from 2 to 5 is equal to 3, find the following. For part A, just know that reversing the limits of integration changes the sign. So the integral from 5 to 1 of f of x will be the opposite of the integral from 1 to 5. Since the integral from 1 to 5 is 5, the integral from 5 to 1 will be negative 5. We know that the integral of f from a to b is the area under the curve from a to b. If we split the interval from a to b up into two subintervals, it would make sense that the integral from a to b should equal the integral from a to c plus the integral from c to b. The total area under the curve from a to b will equal the area under the curve from a to c plus the area under the curve from c to b. Similarly, the integral from 1 to 5 will equal the integral from 1 to 2 plus the integral from 2 to 5. But we are given that the integral from 1 to 5 is 5, and we are given that the integral from 2 to 5 is 3. That means that the integral from 1 to 2 must be 2. So we end up with the 2 plus 3 to equal this 5. So keep that in mind. We now know that the integral from 1 to 2 is 2. You can integrate a sum by taking the integral of each term separately. So the integral of f of x plus 2 from 1 to 2 will equal the sum of these two separate integrals. But we just discovered that the integral of f from 1 to 2 is 2. So this will equal 2 plus whatever the integral from 1 to 2 of 2 is. Here's a shortcut for taking the integral of a constant that I would like you to memorize. The integral from a to b of c will be b minus a times c. I'll explain why that is in a minute, but going back to the integral of 2 from 1 to 2. Using the shortcut, we will do 2 minus 1 times 2. But this is just 1 times 2, which is just 2. So the final answer for part B is 4. Now let me do a quick side lesson to explain why the integral of a constant from a to b is b minus a times the constant. One way to understand where this shortcut is coming from is to think about it geometrically. We know that the integral of a function from a to b is the area under the curve from a to b. But if the function is a constant, graphically that's just a horizontal line at c, or whatever the constant is. So the area under this curve from a to b is a rectangle. So this area, we know the area of a rectangle is base times height. The base of the rectangle will be b minus a, the width of this interval. And then the height of the rectangle will be the value of c. So that's one way to understand where the shortcut is coming from. The other way to understand is to go ahead and take the definite integral of the constant. We know that the antiderivative of, let's say, 5 would be 5x. The antiderivative of c will be cx. However, this is a definite integral, so I'm going to add the limits of integration from a to b. To evaluate an antiderivative from a to b, you plug in the top minus plug in the bottom. So plugging in the top for x would be cb. And then minus plug in the bottom, and plugging in a for x gives us ca. But guess what? We have a common factor of c. So we could factor that out and get c times b minus a. Of course, this is the exact same thing as b minus a times c. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.